Alright, so as I mentioned at the end of the last video, we're going to start building our conversations now about mechanical energy, building all the way up into probably the big topic in this unit of conservation of energy. And then we'll have one short little topic about power. So mechanical energy. So the mechanical energy, right, of a system is simply the sum of kinetic energies and potential energies of that system. So oftentimes mechanical energy is referred to as total energy. So if you see that in a problem, that's what they're talking about. These are one and the same. Now mathematically, essentially, what does that mean? So our mechanical energy is going to be represented by E. It's going to be the sum of our kinetic energy plus our two potentials. Now what happens is, sometimes though, in problems you may not have a spring, so if there's no spring involved, your total energy is just K plus UG, right? Sometimes you don't have a height difference, so your total energy would be K plus US. So if you had a spring, if you had a spring on a table, right? So if I had something like this, spring attached to the wall and the table, I know not a wall, but a spring is attached to the wall, right? My table was bad. They weren't on the spring. The block was not on the table. So let's do that. All right, close enough, right? And so it's able to move back and forth, right? So there's no height difference. So I'm going to not have to worry about that, or not have to worry about US. But there is for example, if I have a vertical spring allowed to move up and down, right? And if my measurements are taken from the floor, then I probably would have to do all three, right, to find my total energy. Okay, and that's again, as long as this is moving, right, it would have kinetic energy. As long as there's a height difference, it would have UG, and as long as there's a spring involved, it would have US. Okay, and so that's why you would have all three in that situation. Alright, so now here are some example problems, right? So the first one is going to talk about a satellite in orbit around the Earth. Has a mass of 2,755 kilograms and moving at a speed of 7,800 meters per second. If the satellite is orbiting at an altitude of 300,000 meters, the acceleration to gravity has a value of 8.94, which is lower than at Earth's surface, as expected. How much mechanical energy does the satellite Earth system have relative to the surface of the Earth? Okay, and so here's a picture. So they're saying that our h equals 0 is the surface of the Earth, and this is going to be the 300,000 meters, right? And there's our satellite. And so all we're going to do here is just simply calculate the mechanical energy. So we're going to do E equals K plus UG plus US. Now I know some of you are saying, hey, there's no spring involved, so why did we even write that? This is just how I like to do the problem solving. I like to put it all out there together and then cancel as needed. Now, there is no spring. It would be really cool to see a spring be able to travel on the Earth and see how this satellite reacts with the spring. But in this problem, there is no spring, so I can cross that out, right? It's essentially equal to 0. And so my total mechanical energy will just be the sum of my kinetic plus my potential. So it's going to be 1/2 mv squared plus mgh. Now, they don't give you the mass of the Earth because that's not what we're focusing on. We're focusing on the satellite. And so I'm going to now do 1/2 times 2755. That's the mass of my satellite. It's moving at 7,800 meters per second. Right? And then so I got my 2755 times 8.94. Now it's not going to be 9.8 because they give us the G value. And this is going to be 3 times 10 to the 5th. I'm going to write this in scientific notation to save some space. All right, and so for this one, you're going to get a big number, right? You're squaring 7,800. You're at a height of 3 times 10 to the 5th meters, so you're going to get a big number. So don't be afraid of that. So make sure you're writing scientific notation. And so as I plug this into the calculator, I'm going to get an energy of 9.12 times 10 to the 10th joules. So 91.2 billion, right, joules is how much energy this satellite has at that location. Okay. Now, if you lower it, right, it's going to probably have less, right? Lower the same speed, or and so forth, right? So if I move that satellite down in orbit to, let's say, 250,000 meters, I'm going to have less energy. Okay. Next question says a bag of apples with a mass of 2.25 kilograms hanging from a spring scale in a grocery store. The bag of apples stretches the spring and the scale by 3.5 centimeters. So again, we might as well just do this right off the bat. This has to be 0.035 meters. The spring has a spring constant of 450 newton meters. The bag of the apples is 1.2 meters above the floor. How much mechanical energy is in the bag, scale, earth system relative to the floor? So here's a picture. Here's my bag of apples, my spring. And so they're saying that this spring stretches that 3.5 centimeters or 0.035 meters. It's at a height of 1.2 meters, right? And because they're saying relative to the floor, which this is my h equals 0 point then. And so all I'm going to do is simply add UG plus US, right? It tells us that it's at rest, right? Or once you put stuff on a spring scale, it rests at its weight. And so now I'm just going to do mgh plus 1/2 kx squared. Those are my two equations. And so I have a 2.25 kilogram bag of apples times 10 times 1.2 plus 1/2 times 450 times 0.035 squared. And so that's how much energy will be stored. Okay, and there are going to be 27 joules of energy stored in this system, right? And so they're talking about this whole thing here would be our system. All right, next question is related to this apple question. So suppose a heavier bag of apples with twice as mass is hung on the same spring scale, causing the apples to move closer to the floor. Would this increase, decrease, or not change the mechanical energy of the system? So let's just say that the apples or the gravitational potential energy stays the same, right? Because the factors are going to equal out and change and all that. So let's just say that stays the same. What happens is then the spring stretches further, right? So the spring stretches further, which means the US will increase. So what does that do to the system? It also increases. Now, we made the assumption that the potential energy will remain the same, or the gravitational potential energy will remain the same, but that will probably also, right? Even though mass and height have an inverse relationship, right? Does it really mean that this is going to even out in a sense? Like, can we actually say that the potential energy will increase or decrease? More than likely it would stay the same, right? Because they're going to balance out, right? So if I'm going to double the mass, I'm probably going to have it's going to go to half the height. Okay, but again, there is that factor of the spring in there. And so regardless, because the spring is stretching, right, it'll probably increase the system because of the energy of the system, because you're going to square a larger x value. Okay, so now we talked about mechanical energy. I know for some people this may not make sense at this point in time, because like, what are we really going to apply this to? We're looking at, a satellite moving around the Earth. We're looking at a bag of apples. Like, how does this really apply to energy? And so you can see kind of popping out the bottom of the screen here, we're going to focus on conservation of mechanical energy, right? And so that's going to be the focus of our next video, which is going to be very heavy on examples.